Alright, so in this video I'm going to talk a little bit more about tension. And how we're going to deal with tension in this class is simply that it is a force that is exerted by a string. Now there is tension within a string, so if I were to say hang a weight from the ceiling, there would be a different tension down here than here just based on how much weight is pulling down on the string and how much weight is in the string. But we're not really going to be dealing with tension in that way. So you can just think about it as a generic like applied force, except that it just so happens that it's by some sort of string or cable, right? Now we've been dealing with problems already where we have forces that are up and down and either accelerating or in equilibrium. But now we're going to look at a little bit more detailed problem where we have multiple dimensions. So let's say I have a stoplight, this, and let's say the stoplight is hanging from two cables, and the cables are each at an angle of 37 degrees. And let's say that the stoplight weighs approximately 150 newtons. Could I figure out what the tension in each one, or the amount of tension in each one of these cables holding up this sine R? And the answer is yes. So I just have to note that this thing is in equilibrium, right? So if it has one force going down, which would be its weight, it would have to have an equal force up that is being actually shared by these two cables. And it will be shared evenly because the angles are equivalent to one another. So that means that this cable would be supporting 75 newtons of the force, whereas this cable would be holding up or contributing another 75 newtons for a total of 150. So 150 up and 150 down. So now we just have a simple triangle problem, right? I just need to figure out, well, what is my hypotenuse? Because this would be my force tension, and this would be my opposite. So I could just say that the sine of 37 is equal to 75 over h. And if I plug that into my calculator, I just take 75 and divide it by the sine of 37, and I get 124.62 newtons. So the actual force tension in each one of the cables would be 124.62 newtons. Right. Now let's look at another example of a problem where we actually have cables going in different orientations. So let's say I have a cable here and there's a sign and there's a pole attached to a building. There's another cable here, right? So I've got the cable pulling up in this direction, and then I also have it pulling away in this direction. Now we can say that this angle, let's just use 37 degrees again, why not? And let's just keep the same size sine, so 150 newtons. Now again, this object is in equilibrium, right? So I very clearly see that there's a force to the left, right? We also know that there is going to be a force down. So if I were to draw just my free body diagram, I would have my weight down. I would have F tension, let's call it F tension 1 because it's, going over here to the left. And then I would have up in this direction F tension 2. So how does it make sense that this is in equilibrium if I have this object or if I have this tension that's at an angle? Well, basically, if we look at this, we know that it has both a horizontal and a vertical component, and that horizontal and vertical component must be equivalent to this. So I must have a vertical component of the tension here and a horizontal component of the tension there, so such that FT1 would be equal to the FT2, I guess we could say x component, so I'm saying this is FT2x, right? And that the FG, or the weight, is equal to, we would say, like the FT2y component. So the second tension force is y component, right? So could I figure out what the tension in this string and this string are? Well, I know that they are equal to one another. The only number I really have now is weight, right? 150 newtons. So just here, I can see that I know that both of these have to be 150 newtons. And again, I have a right triangle. So if this is 150 newtons right here, and I know this angle, again, I just have a trigonometry problem, right? So again, this is the opposite, and this is the 37 degrees, and this is the tension, the string tension. So in this case, I'm going to say the sine of 37 is equal to opposite, which would be 150 this time, over the hypotenuse. So if I were to solve this, I would get 150 divided by the sine of 37, and I get 249, which is about double the last, which makes sense. So this tension would be 249 newtons, roughly. And then to the left here, I have this FT1, which is equivalent to this x component. So I guess I just have to use trigonometry then to figure out what is this x component. And I know both of the other sides, so I could use cosine or I could use tangent. But let's just go ahead and use cosine. So the cosine of 37 is equal to, I know my hypotenuse is 249, and now I'm trying to find my adjacent, which is my FT2x in this case, or which is equivalent to my FT1. Right? Let me zoom out a little bit so you can see that. So I just take the cosine of 37 and multiply it by 249, and I get, it's about 199 newtons here. Right? So when solving equilibrium problems with tension at different angles, it's all about drawing a free body diagram and then, ultimately recognizing what components are in equilibrium with the x and y's, and separating them into the horizontals and the verticals and just setting up equivalencies. Okay. So hopefully this will help you to solve a little bit more advanced tension problems. In the next video, I'm going to talk about Atwood machines, which are using strings and pulleys.